Welcome back. This is part two of the mathematics in molecular orbital theory. And if you recall from the last section, I just completed building a matrix for a very simple chemical system, 3 carbons in a row. And when I did the matrix, I was able to find that the equation of that matrix is x cubed minus 2x, and that's really equal to 0. So the question now is, can I solve for x? The answer is yes. I mentioned that I have a 3 by 3 matrix, so I should have 3 roots. And when I plug this thing into my Newton's equation solver, I got 3 roots. One of them is 0, one is 1.4142, and one of them is minus 1.4142. And I encourage you to try to make sure you can find those roots as well. Okay, so what we've been saying all along is if we can solve these matrices, we can find the value of V. Now, okay, what that really means is I can find the relative energy levels of E. I'm not going to be able to find a specific number like minus 60 kilocalories, but I'm going to be able to find some of the relative energies. So this thing x I can replace with this mathematical formula, and that's alpha minus E over beta. So if I were to go back to, let's go back to my two carbon molecule, what you should be able to see there is I can substitute in alpha minus E over beta, okay, and alpha minus E over beta. And for the ones, they're going to be just beta, so I'm going to put beta there. And if there's a 0 there, that would be a 0. And all of that is equal to 0. And the question you may now be asking is, what are alpha and what are beta? And alpha and beta are basically energy coefficients, energy values, and it's going to be the case that alpha is going to be a relative constant for most systems, but B is going to vary. And by the way, some of you who have come across the concept of resonance, okay, sometimes we'll call beta the resonance integral. Okay? But really what I want to know is what is the relative contribution of beta to the energy of the molecule. Okay, so let me switch papers here. And so I'm going to go back to here, x and 1, 1 and x. This is for my 2 carbon system. Okay. And what I came out of that one was x squared minus 1 equals 0. When I do the cross multiply, there's x squared. Okay, and I subtract the reverse weave, so that's 1 times 1. So all that's equal to 0. And I think you should be able to find that x is equal to plus 1 or x is equal to minus 1. If I plug those values in there, I should be able to get that in there. Okay, so if plus 1 is equal to minus energy over beta, or minus 1 equals alpha energy over beta, okay, I should be able to solve for, if I do the algebra here, okay, I multiply both sides by beta here, okay, and if I put the energy on the one side, okay, I get that as being a value for one of my energy values. If I do the same here, multiply both sides by beta, I get negative beta is equal to alpha minus E, or E equals alpha plus beta. Okay, so what I've just been able to do is I've just been able to determine, I've solved for E basically, I've determined the energy levels, if you will, for this pretty simple molecule. Keeping in mind, what have I not included here? I don't have any hydrogens, okay, I don't have a whole lot of things here, so this is a pretty simple idea. What I hope you are getting the idea on for a bigger system, that obviously the mathematics is going to get significantly more complicated than this. You're not going to be able to do this by hand, but I'm anxious for you to be able to see a very simple, actually very simplistic example of some of the mathematical gyrations that the computer does go through, and how that affects each other. Okay, so what that means is, if I build me an energy diagram here, and energy is getting higher here, okay, what this is suggesting to you is that you really will have two molecular orbitals, okay, or MOs. And let me make the point here that you started with two atomic orbitals. Remember psi 1 and psi 2. You added them together and you multiplied each one by some coefficient, which we'll talk about here momentarily. Okay? And the method you're using here, by the way, is linear combination of atomic orbitals. Linear combination is simply a fancy word that says add these guys up. So I took two atomic orbitals, okay, and I added them together, and that gives me the total, okay, what's called the molecular orbital. Okay, that gives me the molecular orbital for the particular molecule. Okay, now it turns out obviously nothing is this simple. So the rule says I count how many atomic orbitals I have, and there's one atomic orbital, two atomic orbitals. Basically, if you count how many atoms you have, that's how many atomic orbitals you have. And if you have two atomic orbitals, by definition, by the rules of quantum mechanics, you have to have two molecular orbitals. Okay, so I'm going to have two molecular orbitals, and some of you have seen these. This is energy going up on the y-axis there, and some of you have seen these filling diagrams. Well, I'll put a couple of electrons here, and if you read the chapter reading this week, if you look at the podcast, the main podcast for the week, you'll get a chance to learn a little bit about how electrons fill. And the question is, okay, what you should notice here is this is a low energy orbital, and this is a higher, I don't want to say high, but a higher energy orbital. Okay, and in this particular case, this one is filled with electrons. Okay, this one is unfilled with electrons. And if this were the highest one that's occupied, we would call this the HOMO, highest occupied molecular orbital. And if this is the lowest one, that would be called the LUMO. It turns out that in molecular orbital theory, this gap, the difference between these two energy levels, okay, that gap there has some real significance, okay, and we cleverly call this the HOMO-LUMO gap, okay, and that's what that's called. And depending on how big that gap is, what the size of that gap there is, that's a delta there, so the size of that gap there tells us a whole bunch of things about the behavior of the molecule. So this is sort of what we're trying to get at, but what we need to do is, let me switch papers here. Thank you, I switch. Okay, let me go back to my diagram here. Okay, this is my energy diagram. You're going to see a lot of these. Okay, so I've got one molecular orbital here and one molecular orbital here. I'm going to call this psi molecular orbital 1, and I'm going to call this psi molecular orbital 2. Okay, I think I said that the psi for the whole molecule was this coefficient times the baby psi plus the other coefficient times the baby psi, and it's actually a little bit more complicated here because this total molecule is actually a combination of 1 and 2 as well. Okay, and the question is, what's the energy of these two orbitals? Okay, well, we found out that the roots of the equation that we just did, remember that was +1 and -1. Okay, So the energy is going to be equal to the sigma value, which is a constant, okay? And it depends, the constant value depends on what the system is, okay? Minus, okay? And it turns out that beta, okay, is a negative number. Okay, when I've actually figured out it's about 60 kilocalories per mole. Okay, about 60 kilocalories per mole. Okay, so this first energy here is going to be alpha plus beta. Okay, so because, okay, suppose this number is 100, and then what we're saying here is we're adding plus a minus 60. Okay, so that total number there is going to be a 40. Okay, here we're going to say alpha minus beta, and again, let's assume alpha is 100. I'm just making up a number there. That's going to be minus 60, and minus minus is a positive, and so that's equal to 160 energy units. So this first energy level is always going to be alpha plus beta, and that gives us a total energy value of about 40. And again, that's simply by assuming that alpha has a value of 100 kilocalories per mole, and beta has an energy value of minus 60 kilocalories per mole, gives me a total value of 40 kilocalories per mole and 160 kilocalories per mole here. Again, I'm just making up that 100 value right there. Okay, so okay, what this tells me here is that the HOMO-LUMO gap here, okay, if I subtract the LUMO minus the HOMO, weird sounding language, doesn't it? Okay, and the LUMO is a minus 1, okay, because I had a minus 1 here, minus a positive 1, and I got that from the roots. Okay, so the total delta there is about, excuse me, is about minus 2 beta. Okay, and that tells me the relative size of that HOMO-LUMO gap there, which again has implications when I get into trying to figure out what's the behavior of this molecule, and goes from there. So what's happening here is we're simply trying to determine what the relative energy values are of this energy, partly so I can say something intelligent about what the HOMO-LUMO gap here looks like. What's the difference between two particular orbitals? Okay, let's do one more quick example. Let's go back and look at the, get that turned off, there we go. Let's go back and look at this thing here, and I think I had for my function x cubed minus 2 is equal to 0. And when I put this into my Newton's equation, I got x equals 0, x equals 1.4142, and x equals minus 1.4142. Okay? And what that means is I'm going to have psi 1, psi 2, and psi 3. Okay, and each of those is going to have an energy, so basically I'm computing the energy of each one of these now. And they're all going to have some constant value called alpha. And they're all going to have this beta resonance integral thing. Okay, the question now is what value goes here, here, and here? And again, using the same idea I used before, this is going to be a plus 1.4142. What would be the next one? Okay, this one is going to be a minus 1.4142, because remember, this is a positive number times a negative number, okay, and a negative, and that's going to give me a, okay, this is going to give me a low value of energy. This is going to give me a high value of energy. Okay, and what do you think the one in the middle is going to be called? Okay, that's going to be called 0. Okay, that's going to be called 0 because that's my third root up there. Okay, so that one's just going to be something like that. And what that tells me, okay, is if I draw this on the energy diagram, Okay, there's a molecular orbital. Okay, there's a molecular orbital, and there's a molecular orbital. And this is psi 1, this is psi 2, and this is psi 3. And this one's just going to be equal to alpha. This is going to be equal to alpha plus 1.414 beta. This one is alpha minus 1.414 beta. And it turns out that if we have one that's just an alpha, we call that a non-bonding orbital. Okay. These one, in this case, this would be the LUMO, this would be the HOMO. Okay, there will be nothing happening in there. Okay, and we would look at that energy difference right there to figure out what our HOMO-LUMO gap looks like. So this is the fundamental underlying mathematics of how you do what the computer is doing when you're building these molecules and telling it to hit the run button. So I'm anxious for you to be able to do some of these things by hand. And in one of the labs this week, okay, you're going to take this even further. Okay, so suppose you have a molecule, okay, that has 4 carbons in it, and in this case it has alternating double bonds. Because it has alternating double bonds, we call that conjugated. And we're also going to call this a non-cyclic, meaning it doesn't go in a circle, it's linear. Poly, meaning more than one atom. Ene, and an ene means it has more than one double bond. So this particular molecule is called butadiene. Okay, buta because it has, but means 4 carbons. Okay, di means 2, ene means double bond, so but 4 carbons, di 2 enes, 2 double bonds. Okay, butadiene. That is a non-cyclic or linear polyene. And as you're going to see in the lab here that you're going to do is we want you to figure out, okay, so I'm going to call this molecule atom A, atom B, atom C, atom D. So alpha 1 is Ca1 times alpha of A plus Cb1 times alpha of B times C1 alpha of C plus, I'm running out of room here, plus Cd1 alpha of D. Okay, and what I'm going to ask you to do is to be able to calculate these C coefficients here. Notice that it gets very complicated very quickly when you have more than 2 atoms. And the way you're going to calculate your coefficients is in the lab. I've given you a formula, and it's going to look something like this. And you're going to use a spreadsheet to do this. And in this particular case, n is equal to the number of atoms. Okay, so in this particular case of butadiene, it is equal to 4. J is the number of the wave function. Okay, so there's J equals 1, there's J equals 2, there's J equals 3, and there's J equals 4. Okay, and R is equal to the number of the coefficient. And it's always going to be a square, so notice 1, 2, 3, 4, 4, and this is 1, 2, 3, and 4. So notice we have another nice matrix here, except it's a 4 by 4 matrix. Okay, and so you're going to use this equation here, okay, to try to find all the individual coefficients for that molecule. You can also, okay, we also ask you in this lab to be able to do this. Okay, and we've already done this. We calculated M for C, 2 C's. We did it for and in this case m was equal to 1 and minus 1. Here m was equal to 0 minus 1.414 and 1.414, 2, 2. And we give you a formula to be able to calculate that as well. And we're asking you to try to do this on a spreadsheet. And this should be pretty straightforward, okay? So m is equal to 2 cosine j of pi n plus 1, okay? Where again, j is wave function 1, wave function 2, wave function 3, wave function 4. And I think I'm asking you to build a spreadsheet that can calculate these things for anything from n equal 2 to n equals 6. Okay, so hopefully these podcasts will help you a little bit with especially this first lab here, where we're asking you to calculate the atomic orbital coefficients for these non-cyclic polyenes. And I'll ask you to read very carefully the lab instructions because it explains a little bit about the math here. We'll give you a picture here of what these functions look like, and what I hope you will come to understand is, notice, by the way, let me repeat that we're ignoring all the hydrogens here to simplify our system. And what I hope you appreciate is how complicated the mathematics is becoming for what is considered by chemists to be an extremely simple system. Okay, that's a very simple chemical system. And what we are asking you to do in the lab is to be able to come up with a spreadsheet. Here's an example for 6 carbons. Okay, here's an example for 6 carbons, where we're asking you to come up with, these are all the atomic coefficients for a 6-carbon non-cyclic polyene. Here's my energy levels, and we'll talk about what those mean at the appropriate time. But at this point, we simply want you to be able to calculate them using a spreadsheet. So that's it for this second half of this podcast. We'll see you online. Thanks very much.